Good morning. Welcome to your first lecture on cable-stayed bridges. We will, in this your seventh semester and your eighth semester, cover the whole area of cable-stayed bridges. In this first semester, we talk about cable-stayed bridges in the final stage, from all aspects, from basic design ideas to some aesthetic guidelines, over an outline of all the structural parts and details and systems. And then we do some preliminary calculation by hand. You could do them with a slide rule, the way I started my structural engineering 40 years ago. So it's very basic, but that will enable you to understand the flow of forces and how to put the thing together. Now, in the next semester, we will then talk about the construction of cable-stayed bridges. This is, for a practical engineer, at least as important, the construction, as the final stage. When we start designing a cable-stayed bridge, we have always, from the very beginning, have to consider in the back of our mind how to put the thing together. In what are the circumstances, what makes it special. So, this semester, the final stage, next semester, construction, including construction engineering, how to calculate the intermediate stages. Now, there are scripts in English for every lecture. What I'm trying to tell you here is a somewhat little bit simplified and I hope more entertaining version than what is in the scripts. You can load them down, and of course it would be ideal if you listen to the lecture where I try to give the broader picture and then read it in a little bit more detail in the scripts. If you have questions or comments on what I'm telling you, let me know. There's my email address, and you're welcome to write me an email. Also, I'm more than happy after the lectures to stay with you and get your feedback on what I'm telling you. I'm a practical engineer. I've worked 40 years on very much designing cable-stayed bridges all over the world with a consultant, Leonhard Andre and Partner. And so although this is my third year, I'm still new in the business of teaching, and therefore I'm very interested in any comments you may have. Now, that as an introduction, and now we go into the things we consider the basics of cable-stayed bridges. We will talk, after a general introduction, on the overall system, on tower shapes, on beam cross-sections, on stay cables, and we'll try a little summary. So this first lecture should give you then the basic idea, what is a cable-stayed bridge, what are we talking about? Where is a cable-stayed bridge positioned in between the other bridges? Now, span ranges of cable-stayed bridges may go down low to, say, 100 meters with one tower only, and go up to over 1,000 meters. The world record now is 1,088. At the lower end of the spans, of course, there are arch bridges, and there are girder bridges, haunch, continuous beam bridges. Above cable-stayed bridges, above 1,000 meters, there are the suspension bridges, where the world record is now 1,990 meters. So the cable-stayed bridges cover a broad range of spans between 100, 200 meters, maybe in cases up to more than 1,000. What are the advantages of cable-stayed bridges? What has caused that they are so widespread, used all over the world, say since at least the 70s? They've mushroomed, and sometimes I've said with a little smile, currently cable-stayed bridges are the most sexy bridge type in the world. All bridge engineers are interested in them. Well, first of all, naturally, if we compare with a beam, we take off the big moments of a beam by supporting the span with the cables, so the moments are very much reduced and we can use much thinner beams with much less depth. The second advantage is the ease of construction. Cable-stayed bridges lend themselves to free cantilever construction without any auxiliary supports. Comparing the construction of an arch bridge, we have to support somehow the arch until it's closed, because the arch is only working when it is continuous and can carry the compression and can anchor the horizontal force here. We can tie them back, we can support them various methods, but the flow of forces during construction of an arch is distinctly different from the flow of forces in the final stage. Similar to so-called self-anchored suspension bridges. When suspension bridges are very high above water, we cannot anchor the cable forces, the horizontal components, in abutments. They would be very heavy, very expensive. So we anchor them in the beam, so-called self-anchored suspension bridges. Now, self-anchored suspension bridges do only work when the main cables plus the beam is completed, and therefore the beam has to be temporarily supported by auxiliary piers. Completely different flow of forces during construction and in the final stage. Differently for cable-stayed bridges. Now, cable-stayed bridges carry their loads in the cables back here in compression in the beam. And when we have initial systems, we free cantilever them to left and right, and we have the same flow of forces in these construction systems than we have at this location in the final stage. We take loads, dead load from the beam, in the cables, and we have the same here, and so the horizontal components equal one another out. We do not need any auxiliary supports for cable-stayed bridges for their typical construction method of free cantilevering outwards from the towers. And third important example is their bigger stiffness. Cable-stayed bridges are inherently stiffer than suspension bridges. We have a similar bridge and place a load there. A suspension bridge will deflect much more than a cable-stayed bridge, which has to do that a suspension bridge can form its equilibrium by just finding a new equilibrium, whereas stay cables have always to elongate in the place where the load is. And so more stiffness also means a higher aerodynamic stability. You know, when the strong wind is coming and the beam starts to flutter, we will see later, we have 2 lectures on bridge dynamics, and we will see the Tacoma failure, the movie. So this fluttering of the beam, which has destroyed early on many suspension bridges. depends on the frequencies, and the torsional frequency is the higher, the stiffer the bridge is, resulting in the following. If we look into this graph, and we have here a main span for a similar suspension and cable stayed bridge, and have here the critical wind speed in which the bridge starts to flutter. Then if we compare for a main span of 500 meters, then a cable stayed bridge, or we can start here, the suspension bridge, will start to flutter at about a wind of 100 kilometers per hour, and a cable stayed bridge will start at a wind speed of about 200 kilometers per hour. That simplified example shows you how this improved stiffness of cable stayed bridges results in the important higher aerodynamic stability, which for spans up 500 up to 1,000 meters is one of the main problems. So these are the advantages of cable stayed bridges, in addition to a very economic use of material. So finally, I mean, that's the name of the game for practical engineers, we must find the least expensive design in order to win the competition to have our bridge built. And that has shown in their span range, cable stayed bridges are the most economic bridge system. Now, the development of cable stayed bridges just shown by the development of their main span length. There was nothing virtually, we'll have in the second lecture today, the beginnings of cable stayed bridges, but it took on after World War II in the 50s with mainly first with bridges in Germany and so on. And you see here that's the main span. The spans developed in a rather straight, or you could even see an exponential function, up from 300 to 300. The majority is in the range between 100 and 400 meters. But we are now up with Sutong and Stonecutter well beyond 1,000 meters. All those bridges will be shown in detail during the run of the next year. So you see, it's like an explosion from the 70s, how this bridge system developed in main span length and in numbers. We had in the 80s or so, we had about 100, 150 major cable stayed bridges known worldwide. And now we are definitely above 1,000, and there's nobody who can really pinpoint which they are. It's just an estimate. In the book I've given you, and what I'm telling here, we treat about 200 different cable stayed bridges in one way or another. Now, particular to a cable stayed bridge are the stay cables. So, stay cables, we look at first of all how we can arrange them. Now, it's all started with single forestays and backstays, which somehow replaced a pier which could not be placed, or it was less expensive to do it this way. And then the development went from single stays, forestays and backstays, to several forestays and backstays, providing smaller distances here, until today we have what we call multi-stay cable stayed bridges, where we have the stay cables, many stay cables at close distances. So, from single individual cables over several with distances of say 40, 50 meters at the beam, to multi-stays with distances in the range of 10 meters at the beam. We can arrange these cables in basically two shapes. The one shape is where they all meet at the tip of the tower and radiate out. So it's called a fan system. You know what a fan is if you want to cool, the ladies preferably want to cool themselves, and you can open and close a fan. Ein Fächer. It's sometimes in English also called radial, which is similar, but we stick to the word fan system, Fächer. And the other basic system is where all stays run parallel to one another, and we call that a harp system. You know what a harp and a Harfe. Those are the two basic systems. Real life, as always, or sometimes, doesn't give the pure form. Now, it is very difficult to really anchor many stay cables at one point. Would make it very difficult. So, what happens mostly, we have to distribute the anchorage over a certain area. We need about 1 meter distance to anchor the cables. So we come to an intermediate system, which is basically a fan system, but not all anchored in one point, but from structural reasons distributed. Now, the stiffness of a cable-stayed bridge depends on the stiffness of the cables. The amount by which a beam deflects, if we put a load on, depends to at least 95% on cable stiffness, and only something like 5% is provided by the tower and by the beam. So the cable must be stiff in themselves. Cables are from high-strength steel, similar as post-tensioning steel. And so they have a basic modulus of elasticity of 2.05 times something, like all steel. But we have one additional effect to consider, and that is if we span a cable between 2 points, or if you use a cloth line to hang up your washing, there is a sag in the cable. And now, by pulling at the cable, the sag is reduced. So we have, in addition to the elongation, the elastic elongation of the cable, we have an additional elongation which is due to the reduction of sag. I think it's very clear if you have a short line here between your hands and you pull at it, the sag is taken out, and that can be calculated. One can use basically the stress of the steel, and we have an effective modulus of elasticity compared, which is smaller than the basic elasticity, say, of a vertical cable, in the range of stress to the power of 3. That is important. We need to stress stay cables as highly as possible in order to reduce the sag to a minimum, and by reducing the sag to the minimum, having a nearly straight cable, we have the highest effective modulus of elasticity, or we reduce the basic modulus by a minimum, and this is the formula by Ernst, well known. And if we look into this diagram, we have here a span, say 400 meters, and if we have, and these curves are given for the various stresses in the cables. If we have a low strength steel, we cannot stress so highly as if we have a high strength steel. And here we have the effective modulus of elasticity. The 205 is the straight steel, and if we have, under permanent loads, which is governing, a stress of 680 Newton per square millimeter, which is reasonable, then we see we have very little loss of effective modulus of elasticity. If we have very low strength steel, which we can, or stress not highly, we lose up here 50% and more. Now this is theoretical. Our systems today play in this upper region where we have a little reduction in E modulus, but not very much. It's not really governing the design anymore. Now, another basic question is how to make the spans of a cable-stayed bridge. Normally, what we have is we have built a bridge from A to B, and then how to make the ratio between main span and side span. Basically, I can only do it very quickly here. We do it later in detail. It depends on the stresses in the backstay cable which govern the bridge. And that again depends on the ratio of live load to dead load. And so, just to put it short, if we have a road bridge, concrete bridge with roadway traffic, we have about 25% live load and dead load. And we come to a span ratio of 0.4 to 1. And if you look at cable-stayed bridges, most of them have a ratio of 40% side span to main span. If it would be 50, then it would of course be balanced, but we need a little bit shorter here. If we have railway bridges with higher loads, then this becomes shorter. So that diagram gives us a rational way to determine the span length. There are other factors. If you can't place a pier somewhere, well, you have to do something else and take the consequences by means of more cable steel or things like that. How high shall the tower be? Also, if we make a cost diagram over that is a cable quantity, and here we have a ratio, and then we see the minimum cable steel is required in the range of 0.2 to 0.25. So you will always find it's a rather flat curve. You will find the tower height above deck comes always to about 1/5 of the main span. Now, we know already side span to main span 0.4, tower height 1/5, so we can start designing a working cable-stayed bridge. And finally, we have here from the overall system some support conditions. I'll make that briefly. If we have high longitudinal forces from, say, railway braking, we want to distribute them. There are various ways. We can make it tight here. Then we have a lot of movement here. We can try to fix it to one tower, then all the force goes into one tower. We can try to hang it to two towers elastically. Then the force, the braking force, is evenly distributed. Only we have to take care that if we fix it, the temperature movement of the beam will bend the towers outwards, and that may give them too many moments. So it's a complex system where we have various possibilities. For short bridges, we like to hang them here. If they are not too high, we like to fix them to one tower. If we have railway bridges high up, we may use hydraulic bumpers, which do not react for slow movement in temperature, but react for quick movement of braking. And we can use elastic bearings. Many things we will discuss later in detail. That was the horizontal fixing. Now, vertically, at the end of the bridge, we have to take up the uplift forces from loads in the main span, tie them back, try to turn the bridge around, so we have to tie them back, and therefore we call these end piers, abutments, we call them anchor piers or hold down piers. And the easiest is, here come the cable, we take here a pin and we hingedly connect it to a slender pier which can follow the movements. That's one possibility. Another, used formerly very often, is to make pendulums. We have here the cables coming down and we use a long pendulum with hinges here and there to tie the vertical forces down. Problem is we have from live load compression and tension, so fatigue is a problem. We have to can pre-stress, post-tension them, but basically we have to find some means of vertically tying down the uplift forces there. Now the next basic part is we consider, after we've looked into the stay cables, we now look into the second important characteristic feature of a cable stayed bridge. Those are the towers, which to a large extent with the stay cables give the aesthetic appearance of a cable stayed bridge. The beam is more or less similar and stay cables shall be fine. They are also similar in the two shapes. Now the towers, distinct cable stayed bridges from one another. We have to consider for two cable planes. We've made a mistake there. We can hang the beam up with two cable planes, one at each outside or inside. There we call it one cable plane. If we have the usual two cable planes at the outside, then we can, for short spans and low towers, we can use just posts. If the bridge becomes longer, we connect the posts with a cross girder, with a strut here, and then we have a frame tower. We can then, if the spans become longer, lean the two legs to one another to a so-called A-tower, which and still can have two inclined cable planes, which has advantages in torsional stiffness, we will see later. And finally, if this tower is very high up, then this distance would become rather big. Two foundations independent may be expensive. So a good possibility then is use this A, but pull back the legs at the bottom and have a sort of what we used to call a diamond shape in the US. Germany we could call it a rhombus. So these are typical tower shapes which you will find in many variations for two cable planes anchoring the beam at the outsides. Now, if we have one central cable plane only, which of course is sufficient to keep up the beam, but the beam of course then has to be able to take torsion if we have live load standing only on one side of the beam. It must not rotate too much. So for these types we always need a box which takes the torsion. By two cable planes we can use an open cross section because the two cable planes themselves can carry eccentric load by a force couple. Okay, again, short spans, we have such a pin on maybe heavy piers. If it becomes longer spans, this will be higher. And finally, we can do a combination, so we can support this center mast to which we anchor the one central cable plane on top of an A-tower. These are typical systems. Now, what beam cross-sections do we use for cable-stayed bridges? We have to distinguish by the material, concrete, composite, steel, concrete, composite, hybrid, I will show you, and double stock. Principally, in my lecture, we will treat all materials equal. We will always show how can we do it in steel, how in concrete, how in composite, because there's no preference. It depends on circumstances. What is the right material for a cable-stayed bridge at a given location? Meaning, translated, what is the most economic solution? Because in practical life, I repeat, that's the name of the game. If we design a bridge, cable-stayed bridge, we want it built. And in order to have it built, it must be less expensive than the other designs. So we have always to think what is most appropriate, and therefore I treat the materials completely equal. So we start with steel. Historically, all the first cable-stayed bridges were steel. We have again, like at the towers, to distinguish, do we have two cable planes, like here, supporting the bridge from the outside, or one single? Now, we start with steel cross-section for two outer cable planes like this. Well, then we need two main girders, either open or closed, and we need a orthotropic deck, typical cross-section like this. We can also use a box with two cable planes. It's not always required. However, a box, of course, increases the torsional stiffness, the torsional frequency, and therefore for the very long spans, we may use both the outside two cable planes, which provide us already torsional stiffness, plus the inner torsional stiffness. And so it's not by chance that this is a cross-section for the current world record holder, 1,088 meters Sutong Bridge in China. There are always special things. We have two outer cable planes for the Stonecutter Bridge in Hong Kong, and due to certain reasons, there's a center tower, they need the space, they have put them apart with cross girders. Now, if we have one central cable plane only, I told you already, in order to take the torsion, we need to have a box which is supported in the center by one cable plane. Okay, there are two cable planes, but they are so close together, I call them one central cable plane. How does it look in concrete? Again, two outer cable planes. That means we can have an open cross-section with some sort of a main girder to which the stay cables are attached. In this case, it was a triangle due to aerodynamic reasons, but basically that's what it is. Also, we can have two outer cable planes with a box in concrete, not normally required. In this particular case, Posadas Encarnacion in Argentina, it was helpful because we had a railway line eccentrically. And so we were happy to use the additional torsional stiffness of the box in addition to the two cable planes, again for additional torsional stiffness. Now if we have one central cable plane only, we, again, in concrete also need a box. Now, how to anchor the central cables to a box? I think the most elegant is what the French used first for the Breton Bridge, by at every cable anchor point having two diagonals to which the stay cables are anchored, and the diagonals are post-tangent down to the webs, like shown here. And so we carry the vertical component from the stay cable via the two inclined struts into the webs. Very elegant solution. Composite. What are composite cross-sections? Verbundquerschnitte. Well, we have a steel grid, and on top there we have a concrete roadway slab. Very often used in countries, say outside of Germany, where they don't have the welding facilities to do orthotropic decks, because this is then much more economic than an orthotropic deck. There is one overriding consideration when using composite cross-sections. And this overriding consideration is keep away tensile stresses from the concrete slab. So, in longitudinal direction, we are compressed by the inclined cables. And in transverse direction, if we use two cable planes, then the beam in between the cable planes acts like a simply supported beam with a bending moment which causes the concrete as top flange of the cross girders to be in compression. So, we do not use central cable planes with composite cross-section, because there we would have tension in the concrete slab. We only support them at the outside, where then the concrete slab acts in compression as top flange of the cross girders. That's basically true for all composite cross-sections. Finally, we have bridge systems which I like to call hybrid. Hybrid, meaning generally we have a steel main span, lightweight, and we have a concrete side span to which the stay cables, the side span stay cables are anchored, and this side span acts as counterweight to anchor the steel plus life load main span in the side span as counter. And we see here typical cross-section, example Flehe, Rhine River Bridge Flehe. We have an all-steel bridge in the center, and we have the same shape, but built in concrete for the side spans. So they prevent that the main spans, so to say, sag down, and the side spans going up, they are cantilage. Okay. Finally, we have a double stock cross-section, which is basically a truss, where we have, say, roadway on top and railway at the bottom. We can have that for 2 and 1 cable plane. And very briefly, we have special lectures on stay cables. We have 3 types of stay cables: lock coil ropes, and we have inside PE pipes either parallel wires or parallel strands. And these are the ones which are most economic today and are used worldwide. We see all these in details. They are anchored, these strands, in a steel cylinder with holes and wedges. So that's how they more or less all look. And how are we anchoring the stay cables? Well, to the concrete beam, we very often cast in a steel pipe, thread the cable through, and use some shims to prevent them from going through here. Or in steel, we can extend the web of the main girder by some piece of steel, weld the steel pipe in, and have the same type of anchorage. At the towers, in concrete, we can overlap them, rarely done, I have one example, to anchor them in compression, or we anchor them inside a concrete box. Then we need some post-tensioning to take up the horizontal component. We can use steel plates to anchor them in steel towers, or spread them over the depths there as an intermediate system. So, I have tried in the first lecture to give you the basic ideas what is a cable stayed bridge. And in the following 29 lectures, we will basically elaborate on those points which I have briefly mentioned. So, thank you. This is the first lecture.